Welcome to ECE 302. This is Lecture A8 on mean and autocorrelation function through an LTI system. I'm Professor Stanley Chen. In the previous lecture, we talked about a few things. We discussed what is a wide-sense stationary process, its mean function, and also its autocorrelation function. We started to introduce the idea of linear time invariant system, a well-known concept in an undergraduate course in signals and systems. The question that we are asking is the following. You have a random process x of t. It goes through a system which is characterized by an impulse function h of t, and then you get an output y of t. And in the last lecture, we talked about this convolution operation, which is that your output y of t can be written as the convolution between h of t and x of t. This applies to any random process, but in particular for wide-sense stationary processes, we have some very nice properties that we are going to explore in today's lecture. What we will see is that as you send this random process x of t going through the impulse response, the output, you have this Ry and your Rx can be related through this impulse response. So we want to find out the exact relationship between the two. Furthermore, we want to take the Fourier transform of this autocorrelation function of Ry, and here we want to take the autocorrelation function of Rx to see what is the power spectral density of each. Okay, so today's lecture, the goal is to talk about this particular problem where we assume that y equals to the convolution between x and h. And then we're going to look at the autocorrelation function of y and also the power spectral density of y. Now, on the right-hand side of this equation, you can see that we have Rx and Sx. These are known. This is at least our assumption that we know that they are available. Okay, so this these two quantities came from the beginning of this chapter, where we look at a random process. We say that we can analyze its autocorrelation function if it is wide-sense stationary, and consequently we can look at the power spectral density. In this lecture, we're going to look at the problem where you send this x through a linear time invariant system, you obtain the y. What would be the corresponding expressions for Ry and Sy? So without further ado, let me start by talking about the mean function, because in order to talk about this autocorrelation function, also this power spectral density, we also need to first know the mean function. So what is the mean function? Now, the problem is this. You have this random process x of t going through an LTI system given by the impulse response h. You obtain the output y. We ask, suppose that the input has a mean of mu x because it is a wide-sense stationary process, and hence the mean function will become constant. So you have this mean going through this LTI system. What would be the mean of your output? Okay, so we ask, what is the mean function of the output? Now, since this is wide-sense stationary, what we can assume is that a wide-sense stationary process, as it goes through a linear time invariant system, it should maintain the property of being wide-sense stationary. If this is true, then we should expect the mean to also be a constant. However, what exactly is this constant? This is something that we want to determine. So in this theorem, what it says is the following. You have this random process x of t, which is a wide-sense stationary process. It goes through an LTI system. You use another wide-sense stationary process, y of t, so both are wide-sense stationary processes. We can show that the mean of this y of t is given by the following formula. On the left-hand side, you have expectation of y of t. This is the mean of y. And then on the right-hand side, you have a product of two terms. The first term is the constant, is the input's mean value. It is a constant because x is y and stationary. The second term in this equation is this integral. It is the integration of the impulse response going from -infinity to +infinity. Or in other words, you just calculated the average of this impulse response. All right, so if this is true, okay, of course we haven't proved yet. If this is true, it tells us a couple interesting things. Number one, yes, the mean of the y is a constant as given by this equation. It doesn't really change over time. This is a constant in time. This is also a constant in time because you have already integrated over all the possible timestamps. Now, the second interesting thing to notice is that as you send this y-sine stationary process xt through the linear time invariant system, the mean is there. It's just a scaled version of your original input. So this is your input's mean, and then this is a scaling constant. This scaling constant is completely characterized by the system. So if you have a different system, you will have the different scaling constant, which is the integration of all the values of the system. There is almost no interaction between this x and also this h, because everything has been decoupled into the product of this mean value and also this mean of the impulse response. So this is the mean function of a LTI system. Now, how do we prove it? The proof is sort of straightforward. We just start by looking at the definition of y, which is the convolution between x and h. Then, in order to find the mean of y, we take the expectation of y, which is really the expectation of this integration. This integration is the convolution. It's the convolution between x and h. So now you can see that in this expression, you have an expectation and then there's an integration. And of course, the expectation and integration, we can switch them. And therefore, the expectation, you can go inside, and then you have this expectation of x of t minus tau. Now we ask, what is this expectation? It turns out that this expectation is just mu of x. Why? Well, because we assume that x of t is y and stationary, and therefore expectation of x of t is just a constant for any time t. In particular, for the time of t minus tau, it is still the same constant, which is mu x. So now here you have this integration with a mu x. Of course, you can pull the mu x out, and therefore you can get this integration over h, and then you have the mu. So here's the proof. And let me show you one example to illustrate this idea. So consider a y-sine stationary process, x of t, such that each sample is an IID Gaussian random variable with zero mean and unique variance. So what it means is that you draw the time axis, you also draw the amplitude axis. At every time stamp, you draw an ID Gaussian sample. Okay. So if you go to the other sample, you just draw another Gaussian random variable, another Gaussian random variable, a Gaussian random variable. So every point is independent. Then you send this random process x of t through an LTI system with the impulse response given by h of t. And here is the expression of h of t. So you send this random process where every sample is ID Gaussian. You send through this h of t. You ask what is the output. In particular, you want to ask what is the mean of the output. So without doing any calculation, we can ask ourselves, what do we expect to see? So let's get this impulse response. This impulse response has a shape. The shape of this impulse response is that it has a support from -1 to 1. Okay, anything that's outside this range would be 0. So you can sort of think that anything outside would be 0. For the things that you will have this expression. Now this expression is really a triangle function. All right, why? Because when t is 0, you get a peak, but when t is 1, you get 0. So it is a triangle function. Now with this triangle function here, okay, this is your impulse response. You send some RID Gaussian random process, which is essentially the white noise. You send it through this impulse response. What will be the output? Well, of course, this operation is doing some kind of averaging, because you say that, okay, here is my sample. I want to take the convolution, right? So you set up a window and then you put your triangle here, and then you integrate everything. So this is more or less like an integration or the averaging. It's the weighted averaging using your edge. So now you're taking the average of this Gaussian process. So what would be the output? Well, it has to be somewhat a filtered version. So originally here it will be extremely noisy. Then maybe you will have some kind of averaged version, or the running average version of this input pure noise. Okay, so let's go back to our problem. Our problem is that what is the mean of this y? Well, let's look at the input. The input is what? Well, if you take the expectation of this input, since the input is either Gaussian with 0 mean, the input of this x of t has to be 0, because this is just an ID Gaussian process with 0 mean. When you have the 0 mean, you go through this impulse response, you get some output. The output's mean shouldn't change. The mean should still be what? It should still be 0. So expectation of y of t, according to our intuition here, according to this diagram, it should be 0. Okay, so let's just check our calculation. So the equation says this. You have mu x of t, which is the expectation of x of t, and this is 0. This is given by the problem. Now we want to find the mean of y, which is the expectation of y. And then what? Well, according to our theorem, it is given by the mean, which is mu x, times the integral of the impulse response. So no matter what you obtain from this integration, this mu x is 0, guaranteed. Right? And therefore, when you take this product between mu x and the integral, you will get 0. And therefore, what is the mu y? Mu y is 0 for all t. And this is consistent with our intuition. Here is a diagram summarizing the problem. The gray lines, or these, they are the ID Gaussian samples drawn at different timestamps. And then I apply the function that I have drawn, which is this one. Okay, here is your y. Now, y is given by this orange line, and you can see that it is a lot more filtered version of this gray lines, which are the ID Gaussian noise. As you filter through, you can compute the mean. Before the filtering, the mean is given by this black line, which is 0. After the filtering, the mean becomes the yellow dotted line, which in this diagram it shows that it is also 0, which is consistent with our theoretical prediction. Okay, so we have talked about the mean function, and so the next thing to talk about would be the autocorrelation function. So suppose we have the same setting where your x of t is y-sense stationary. You obtain another y-sense stationary process, y of t. We want to find the autocorrelation function of y. In other words, we want to find this Ry of tau. And let me remind you, in case you forget, Ry of tau is defined as the expectation of y, t plus tau, and y of t. Okay, and this tau represents the time difference between the starting point and also the end point. The theorem here gives us an expression. Although the expression is complicated, we can sort of understand what's going on. The expression includes a double integration in S and R. The dummy variables S and R, they are defined according to the two copies of the impulse response. And then in this integration, you can also see that there is the autocorrelation function of X. Now, the indexes that you are trying to integrate would be S and R, and they are changing according to the dummy variable S and R. So how do we understand this equation here? This equation can be best understood by looking at here. This is there is a pair of operations. The first operation is tau minus R, and this is what? This is the convolution in R. And then you have a plus S, and then once you have this plus S and you have a HS, that is a correlation in S. And therefore, your autocorrelation function of the Y can really be written as an inner convolution between H and Rx, and then outer you have a correlation between H and the product of this convolution. So that is the expression. Now you may wonder, how come you need to have this convolution and also this correlation? Why isn't it just the convolution between Rx and H that will give you Ry? Now the problem is that the autocorrelation function is really the squared version, right? Because you need to, if you remember this autocorrelation function, you're looking at the function itself and the function at a different time stamp, t plus tau. Because you're looking at two functions multiplied together, or in other words, it's like taking a square of those things. One h is not enough, because one h will be used to explain one, the other h has to be used to explain the other y. And therefore, you should expect to have this pair of h. It's no longer just h convolved with Rx. So how do we prove this extremely complicated result? Well, in fact, the proof is not difficult. The proof goes with the following. You have Ry of tau, you can write it as y of t and then y of t plus tau. The order of this yt and y plus tau doesn't really matter because this autocorrelation function is symmetric. Then you put the expectation here, and then inside each of them you have this convolution. This is the definition of your Ry, and this is the definition of Ry evaluated at t plus tau. So you just replace the index. Here it would be t, and here it would be t plus tau. The dummy would be r, the dummy would be r. This is s, this is s. Then what do? Well, then you have a product of the expectation, right? So the expectation can go inside this integration. Then you have double integration hs, hr, and then you have expectation of whatever you want. Okay, so this is an expectation with the x and x. Then this expectation can be written as the autocorrelation function of x with the index being the time difference between this s and this tau and this r. So you have tau plus s minus r. So that would be the gap. And so if you compare this equation here with what we stated in the theorem, you see that we have already proven the result. So let's continue our example as before. We ask, in that case, what would be the autocorrelation function of y? Now, since our problem is RID Gaussian, the autocorrelation function of x is in fact the delta function. Okay, this is a very special property of our problem because it's pure noise. Okay, this is your input. As you try to compute the autocorrelation function, meaning that you shift the thing left or right, as long as you shift this entire a function to the left or to the right by just one time index is completely independent, and therefore you will have a zero correlation. And as a result, the only point that you will get a correlation is that you're overlapping with yourself, and therefore you will have a delta function. So this is something that is immediately available from the prompt. Now we ask, then what is the autocorrelation function y? It turns out that the autocorrelation function y is determined by substituting your Rx with a delta function. Okay, so when you have this delta function here, then you ask what is the integration? Well, the delta function, let's say we do the delta function with your R. Okay, so you do the integration with respect to R in your delta function. Then the R will say that this delta function will say that, look, since this is your dummy variable, this has to come out as your H. Okay, and therefore you are really just shifting your HR towards the new center, which is tau plus S. And therefore you can remove one of the integration, and then the other integration will be the integration over S, and then the thing that you need to integrate will be HS times H of tau plus S. So I did not continue this calculation because the remaining is just convolution. What you should expect to see is this. Here is your H. This is your H of t. Now, what you're doing in this integration is that you just convolve it once. Now, certainly this is not convolution, this is a correlation, but it doesn't matter because this function is symmetric. For any symmetric function, a convolution is the same as correlation. So you do the convolution once, and we can imagine what will happen. If you do the convolution between two triangle functions, it will become something slightly more smooth. It's not a Gaussian yet, okay, but it will be a little bit smooth, and that will be your autocorrelation function y. Now, in case you don't believe me, you can play MATLAB or Python to generate some plots. The gray line here is the autocorrelation function of x, and then the orange line is the autocorrelation function of y. And as you can see, this autocorrelation function of y really follows what we have predicted. So the last concept I want to introduce in this lecture is the notion of power spectral density of a wide-sense stationary process going through an LTI system. So the setting as before is that you have a wide-sense stationary process x of t, you have a wide-sense stationary process output y of t. We claim that the power spectral density of y is given by the magnitude square of your impulse response. Okay, so you have x of t, and then you have h of t, and then you have y of t. Here you have rx, and then similarly you have xx. Here you have ry, and then you want to find sy. And the theorem says here is that you have a j omega, where h of omega is the Fourier transform of your impulse response. You want to find the relationship between your sx and sy through your h of omega. It turns out that the result is that your output power spectral density is the magnitude square of the impulse response. Now you may wonder why is it a squared function of the impulse response, since Sx is just the Fourier transform of Rx, Sy is the Fourier transform of Ry. Why isn't it that Sy equals to the Fourier transform of H times Sx? This is a legitimate question, and the answer is that here you are doing, when you calculate the autocorrelation function y, you're already using the H twice. Okay, it is not that you're looking at H convolved with y, you're looking at H convolved with Rx, and then you take the correlation with H again. And therefore, there are two H's going on as you go from Rx to Ry. Consequently, as you go from Sx to Sy, you will have the square of the H. So how do we prove it? The proof is literally just taking the Fourier transform of your Ry as what I'm showing you here. Now, of course, your Ry is complicated. Your Ry is a double integration in S and in R. But let's just write down the equation and then do some substitution. So when you write down the double integration of Ry, which is this quantity here, you notice that it is an integration in terms of S and R. There is another thing that is outside, which is e to the power minus j omega t. And this is your Fourier transform. And so now if you want to do the simplification, what you can do is to do a substitution of u equals to t plus s minus r. Then what will happen is that your exponential function will take the form of u and s and r. Consequently, this Rx can be simplified to just Rx of u. And then you integrate with respect to S, R, and u. If you look at this expression here, this is complicated. It's a triple integration. However, you can actually simplify it into a product of three individual integrations. The first one will be the integration in S. The second one will be integration in R. The third will be integration in U. Okay, three separate integrations. Each integration is a Fourier transform. Let's say here, this is the Fourier transform of H. And here, it would be the Fourier transform, but you put a conjugate, complex conjugate, because you don't have this minus sign. The last one is the Fourier transform of Rx, which is your Sx. And therefore, you have a product of these two frequency response, or the Fourier transform of the H. That gives you H bar and H. H bar stands for the complex conjugate. When you multiply them together, they will give you the magnitude square. And here it is the power spectral density of your X. And so we have shown this main result that the power spectral density of Y equals to the magnitude square of H times Sx. So to explain all these concepts, the three concepts that we have introduced in this lecture, namely the mean function, the autocorrelation function, and also the power spectral density of the output through an LTI system, I'm going to demonstrate through an example. So in this example, I am assuming a y-set stationary process, x of t, and then it has a correlation function given by this formula. I assume that this x of t will go through an LTI system with the input-output relationship given by this differential equation. So in this differential equation, you have a second-order term on the y, and then another second-order term on the x. And so we ask, what is the autocorrelation function of y? Okay, right. So before we do anything about this differential equation, okay, what we can do is, can we just do some quick analysis of Rx? Now, it turns out that if you have this Rx being the sinc function, you can take the Fourier transform to determine the power spectral density. So we know that from the Fourier transform, a sinc function with an argument of Wt is transformed to this quantity, pi over W times the rectangle function of omega over 2W. This is in the time domain, this is in the Fourier domain. And therefore, if on the time domain, you have the sinc function, if you take the Fourier transform, this will give you this quantity here, which is pi over pi, so you can cancel all these two pi's, and there's a rectangle function of a width of 2 pi. And this is equivalent to saying that you have a boxcar function, and then the width is from minus pi to pi, the height is 1. Okay. So here is your autocorrelation function. If you take the Fourier transform, you get the power spectral density, and this is the power spectral density of X. Now, let's deal with the differential equation. Okay, so when you look at this differential equation, the first thing you need to know is that the differential equation is telling you the input to output relationship. Okay. Now, how do we understand this differential equation? Well, the differential equation, we know that if you take the Fourier transform on both sides, they are going to give you something. That is the transfer function of the system. If you take the Fourier transform, here, first of all, we know that when you take the Fourier transform, all these constants, they remain. If I take the Fourier transform of yt, I will get y of omega. If I take the Fourier transform of dy of y, I will get a j omega and y. Okay, if I take the Fourier transform of d square of y, I will have j omega square of y. So this is your left-hand side. And on the right-hand side, you have 3, you have minus 3, and then you have 6. And clearly this is 6 of x omega. And then here it would be a j omega times x of omega. And then here you have j omega squared and then x of omega. So these would be the Fourier transform of your differential equation. Then you can move around the terms. You can say what is this input to output relationship in the Fourier space. Then you can group all the terms by showing that y over x will be given by all these quantities when they take the ratio. Okay, and this is how we can get to this result. This is defined as y omega divided by x omega. This is the Fourier transform of your differential equation. And we can define this as your impulse response in the Fourier domain, or something we call the transfer function. And so you have 3 times j omega squared, 3j omega and 6, and something in the denominator. So what we can do here is to look at the theorem, right? So the theorem says that as y of omega equals to the magnitude of h omega squared of sx of omega. Now, sx of omega is already determined on the previous slide, so we know this is a boxcar function. So what we need to do is to determine this thing here. This thing is the magnitude square of your h. And what is it? Well, the magnitude square of h can be determined by looking at the magnitude square of this h. So if you want to look at the square, it will be square here. So what is it? You can multiply this complex number by its conjugate, right? So so here is your h of omega. So h of omega, if you want to take the magnitude square, this is equal to h of omega complex conjugate times h of omega. And so now you can have the original thing, but you now take the conjugate. If you take the conjugate, all the minus j will become plus j. The plus j becomes minus j. So you have these two products. When you take these two products, a lot of these terms, they can be grouped together. And it turns out that finally the magnitude square is a constant with respect to omega, and this is 9/4 just for this particular example. All right, and so now what will happen is that you can show that the power spectral density of your y is given by this constant 9/4 times the power spectral density of your x. And then if you take the inverse Fourier transform, you can show that the autocorrelation function of y is given by this scaled version of the input autocorrelation function. Alright, so this is the end of this lecture. We have introduced 3 concepts. The first concept is the mean function as the random process goes through an LTI system. The second concept is the autocorrelation function. As we see, it is a double integration that involves a convolution followed by a correlation. The third concept that we study in this lecture is the power spectral density. Remember that when you look at the power spectral density of the output, it's the magnitude square of your transfer function. And we also show an example of doing all these three together. There is another example in the ebook. I would encourage you to take a look. There you can also see how we can prove whether a process is stationary or not. Now there will be problems for our homework, so I would encourage you to try and let me know if you have any questions. Thank you very much.